Okay, cold medication like Vicks Dayquil often includes the chemical dextromethorphan, I don't know how to say that, which is a cough suppressant. Although these medications are available over the counter and are generally low risk, taking too large of quantities can cause serious side effects. So here, that drug has a half-life of 3 hours. So what this means, having a half-life of 3 hours, means that after 3 hours, your body eliminates half of the current amount. So if a 30 milliliter dose of liquid Dayquil was given, there are 20 milligrams of dextro. And after 3 hours, 10 milligrams would still be in your system. Right? So you take the dose, and there were 20 milligrams in there. 3 hours later, you're down to 10 milligrams in your system. That's the idea of a half-life. So now, how much of the drug would be in your system after 6 hours? So 6 hours is 3 hours after the original half-life. So the point here that they want you to realize is, after 6 hours, you don't lose another 10 milligrams. You just lose half of what was already in there. So because after 3 hours, I was down to 10, after 6 hours, I would be down to 5 milligrams. We just half what was remaining. And so then after 9 hours, we're going to half that 5 that was there after 6 hours. So we're down to 2.5 milligrams. So this is the idea of a half-life. This is how carbon dating works. If you've ever done carbon dating problems, and we'll do some of those later, I'm sure. B part, how many milligrams of the drug will be in your system after 10 hours, and how do you know this? So, again, there's different ways you could think about doing this. For me, I think about making this an exponential equation. So we started off with 20, and then we keep halving it every time the x grows. So getting the correct x here is a little bit tricky. Because if I let x be the number of hours, well, after 1 hour, I don't want it to half yet. I don't want the half to work until I'm 3 hours in. So the way you could think about that is x represents the number of hours, and we could divide the number of hours by 3. That way, once the number of hours is at 3, 3 over 3 is 1, and then we would have 1/2 to the first power, which is 1. So that would be the first time we halved it, would be when x is 3. So here is our equation. And so if I wanted 10 hours in, I could plug in 10 for x. So 20 times 1/2 raised to the 10/3. So if you plug that in your calculator, you should get 1.98 milligrams. So if you think about it, if you plug in 10 there, 10/3 is 3 1/3. So you've actually done 3 1/3 half-lives. So we haven't done 4 full half-lives. We're somewhere between 3 and 4 half-lives that have occurred. Here it says, what's a formula using D of T that gives the amount of dextro in your system after T hours? This is kind of what we did. We're just making it more official now. Writing it as D of T equals, we said the original was 20 times half-life, and that's happening after I had x over 3 originally, but now then we're using t instead of x, so it'd be t over 3. Again, hopefully you see how that t over 3 represents the number of half-life periods. So we've got a little formula that we've created. 20 is the initial amount we started with, times, so when it's a half-life problem, it's always going to be times 1/2 raised to the t divided by whatever the length of a half-life is. Because for different things, like carbon, for instance, it has a different half-life. Whereas this drug, dextro, has a 3-hour half-life. Different substances have different amounts in that half-life. Okay. What percent of the drug remains in your body after 1 hour? So, if you think about it, after 3 hours, there would be half of the original remains because you half this one time. So we know it's going to be a little bit more than half, and we can find that number by plugging in a 1 for t. So think about just this portion, 1/2 raised to the 1/3, right? Because this tells me how much of the way are we to getting this half done. So if you put that in your calculator, 1/2 raised to the 1/3, you should get 0.7937. Which means this is the amount that's still remaining. 79.4% remains, which means 20.6% has been eliminated. Four, write an alternate formula for d of t of the form d of t equals a times b to the t that can be used to model the amount of dextro in your system after t hours. Clearly explain what your a and b values represent in this context. So what they're wanting me to do is rewrite this equation, where instead of the exponent here being t over 3, it wants it to only be a t. They don't want that third up there. So if we think back to our power to a power rules, so this might be a little bit of a review or maybe something kind of a new idea to you. If I had 2 raised to the 3rd and this was raised to the 4th power, I have a power raised to a power. We can multiply those powers. This is 2 raised to the 3 times 4, which is 2 raised to the 12th. So what we're going to be doing here is we're going to be working backwards from this power to a power model. So we're starting here with it being 2 raised to the 12th. The problem here is it's t over 3. So again, just focusing on the exponent. This is 1/2 raised to the t over 3. How could I write that as 2 things being multiplied? Well, that could be 1/2 raised to the t over 3 is the same thing as 1/3 times t. Because what is 1/3 times t? That would be, we could put the t over 1. And that would be 1 times t is t over 3 times 1, which is 3. And so this is 1/2 raised to the 1/3 raised to the t. Right, so I'm undoing this. How it was a power to a power and we multiplied. Now I'm going and writing this as a power to a power. So now it's 1/2 raised to the 1/3 raised to the t. And the reason I can do that is I know what this is. 1/2 raised to the 1/3 on its own is that number we just looked at, 0.7937. And this is still being raised to the t. And then remember, there was still that 20 that was out front. So the formula could be d of t equals, I'm kind of running out of space here. So forgive me for my messiness. Surely you are used to it by now. I've got d of t equals, this is my formula, 20 times 0.7937 raised to the t. So what do each of these represent in terms of the model? So what's the A value? 20. This is our initial amount of dextro. It's our y-intercept. What does the 0.7397 represent? That's the proportion of the drug that remains each hour. The proportion of the drug remaining each hour. All right, hopefully we just saw that on number 3. So the benefits of this versus here, this tells me hourly how much is remaining. Whereas here, this kind of, we have to go 3 hours down the road to understand that another half is missing. But they both do the same thing, just maybe easier to identify from looking at the equation here. 5, customers are instructed to use the medicine as directed. For adults and children 12 years and over, this means you can take 30 milliliters every 4 hours. Suppose you take your first dose at 8 a.m. Using the recommended dose, calculate how many milligrams of dextro will be in your system at various times throughout the day. So at 8, we started with 20. Now what about at 10? So what you could do is you could plug in 2 here for T. If you do that, you should get 12.60. All right, now here's the tricky part. What about at 12? Well, at 12, the amount that was already in your system will have decreased. This 20 will have gone down 4 hours worth, so we could plug in 4 for T. If I plug in 4 for T, you get 7.94. But at the same time, if you're using the recommended dosage like you should, then someone's taking another 30 milliliters of the medicine, which contains 20 milliliters of dextro. So there was 7.94 of dextro already in our system, and we added another 20 to that. So now we're at 27.94. All right, if you want to, pause the video, see if you can figure out how to do the other ones from there. But if not, now what would happen at 2? So for me personally, the way I would do it to get to 2 now, I have a new initial amount. I'm no longer at 20. My new initial is at 27.94. And I'm going to multiply that by 0.7937, and it's been 2 hours since then. So I'm going to raise it to the second power again. I'm starting over because I have a new initial amount. So if I do that, I should get 17.60. And then if I go to 4 o'clock, so again, now I'm going to plug in a 4 here instead of a 2. If I do that, I'm going to get 11.09. But again, somebody has drank another 20 milliliters of the drug, so it'd be at 31.09. And then I would have a new formula. I wouldn't use this one anymore. I would change the initial value to 31.09 times 0.7937 raised to the T. So then if I plug in a 2 for 2 hours later, I'd be at 19.58. And at 8, it would be 12.34 before the dose. But then they take another 20. That puts me at 32.34. Hopefully you can follow that. I know that's a lot to type in your calculator, and I can't show the calculator on here. So here's the quick notes. If you guys want to copy those down. Main takeaway here, when I'm in this form, this lets me know that 7 years is the half-life, right? It's very easy to see that. Or in this case, it's not a half-life because the argument is greater than 1. Right, so if this was less than 1 and it was a decay problem, it would be the half-life. But here, that means it's doubling every 7 years. So that kind of gives you an idea of how often we're doubling. But when it's in this form, right, if I rewrite it, or I can write that as 2 to the 1/7 to the t, and 2 to the 1/7 is this number. This shows me how much we're growing every year. So it looks like we're growing by about 10% a year, 10.4%. This right here, this is very much the, if you've ever looked at a compound interest equation, or if you've looked at like investing early. Dave Ramsey uses examples like this all the time. And this is why they also talk about, even if you're only earning 10% on your money, it's really doubling about every 7 years. Because that 10% you made the first year gets factored into the amount you had originally. So it doesn't take 10 years to actually double. If you're growing by 10% a year, it would only take 7 years. Right, because the money that you earned during year 1 is reinvested. And it also gets to grow. Compound interest, money making money. Anyways, that doesn't necessarily matter right here. But again, because your B value is greater than 1, it's a growth problem. If this number was less than 1, it would be a decay problem. Here in a second, I'm going to put up a picture of the check your understanding answers. So you may want to pause the video, try to work all that on your own first. And then you can check back here to see how you did.